so I'll just get into it. So I'm going to show you some mostly analytical work that Mark and I have done trying to characterize the behavior of a reactive melt transport in a partially molten binary solid solution with a liquid solution. And the reasons we want to do that sort of thing, I'll try to make clear before I jump into the analysis, and we'll move on from there. So I'm going to start with the background. This is mostly motivated by the observation of channels in the mantle at places like the Oman ophiolite, but difficulty in getting mantle channels to spontaneously arise in numerical simulations. Then I'm going to kind of go over a little bit sort of the theoretical framework about reaction fronts and chromatography for people who aren't familiar with chromatography. And then we'll sort of summarize the problem and build up our analytical tools. And the whole idea here is we want to use 1D analytical solutions to approximate how reaction fronts at lithological boundaries might behave in higher dimensions. So as I said, this entire study is motivated by this observation of channels in the mantle. So here from the Kellerman 95 paper, we've got sort of a schematic box of the Oman ophiolite. And so there are these dunite channels that are a conspicuous feature of the ophiolites, and they're out of chemical equilibrium with the surrounding Harzburgite, which made Kellerman and others sort of start to think that maybe there were these high porosity melt conduits that were feeding melt efficiently to mid-ocean ridges before these ophiolites, which are essentially mid-ocean or oceanic crust emplaced on land. And so here's one of the obligatory Oman ophiolite pictures. Actually, Mark Spiegelman pointed out to me that's Peter. So that gives you some of the scale. So you have these things that are much, much bigger than humans, but then you've also got things that are on the scale of humans or even smaller. So these channels come in all sorts of sizes, and they have been squished and rearranged, but if we're thinking about the scale of these mantle channels, they're highly variable. This plot here in the middle shows that the primitive melts that were in these channels, so magnesium numbers greater than 66, were last saturated with OPX at about 10 kilobars, meaning that these channels had to get up to the surface from 25 to 30 kilometers without re-equilibrating with this surrounding material. And there are a couple of mechanisms that Braun and Kellerman proposed in their 2002 paper where all of these plots are from. But one of the popular ones is this porous flow channels formed by this sort of reaction dissolution instability. And this has been modeled. So this is the 1995 paper by Harnoff and others. So this is like all the Columbia work from the past 20 years or so. And she showed that during this sort of decompaction gradient reaction, you could sort of organize your melt into these high porosity channels, is what this plot shows here. And then later, doing similar work with the sort of OPX gradient style reactions, Mark Spiegelman showed that you could get, I believe, 80% of your melt out through the bottom of this box through less than 20% of the domain by the top. And so that is sort of interpreted as this large-scale channelization. But there's some problems. So later models kept improving the description of the problem. So they were accounting for nonlinearities due to variable viscosity in the solids. There's improved models for the uplifting of the mantle, and a lot of these models, in fact, nearly all of them don't result in spontaneous channelization like some of the simpler, earlier homogeneous mantle gradient pyroxene reaction models did that I showed earlier. And so the sort of explanation for this that was invoked generally is that there has to be some sort of heterogeneity. And so this is an example from my advisor of one of such models that does not produce spontaneous channels. So he's got a, this, by the way, I'll help you out, that's porosity. They didn't label it, and good for them. But this is the porosity field, and through time, there's no channelization form, but instead you kind of get this regularly spaced compaction wave pattern, but no channels.
Is there temperature in that one? And do you remember what is it?
This paper here, like, do they keep track of temperature?
Well, I just recall one of Katz's papers when latent heat was one important process that prohibited channelization.
We're gonna get to that real quick. So then one of the ways to deal with this heterogeneity and thinking about melting of fertile lithological heterogeneities was to couple these mantle models with some sort of model for mass and energy transfer via some sort of phase behavior, like you were alluding to. And some of the kind of general rules of thumb I've listed right here is that the melting rate increases with upwelling rate. So if you're pushing your mantle up, the adiabatic decompression can go faster and you can melt more. The melting rate increases with thermal diffusivity. This makes sense. You can diffuse heat into your fertile heterogeneities. They'll melt more efficiently. And then melting is inversely proportional to the latent heat of fusion, which makes sense, right? So that's like the toll you have to pay to switch phases. So I think that's what you were alluding to. And so this is the Hewitt 2010 model, where he shows that can use some sort of upstream, and by upstream I mean down here, heterogeneity to trigger melt channelization. And then another one, this is Katz and Weatherly 2012. They show that if you have a fusible enough heterogeneity, right? So if the latent heat of fusion is low enough, you can provide an upstream melt flux that's great enough to get things to reorder into channels. So I think that's what you were alluding to, Garrett.
I was just wondering why the Hessedal didn't produce channeling. What was the main cause?
They basically got compacted out, is the way to think about it. Before they could like form and stabilize, they'd get smushed. And that's why you ended up with that checkerboard pattern of waves. And so now there's just sort of this view of the mantle. Here it is kind of in a box. These are plates here, oceanic plates, that you can kind of see in relief, and the white lines are the flow lines, and this is more molten stuff. So this is a porosity, a log porosity plot from a Katz and Weatherly paper once again, where melting and channelization during all of this flow is presumably aided by fusible heterogeneities providing an enhanced upstream melt flux. Okay, so I'm going to switch gears a little bit and talk about chromatography. And this is how we're going to frame thinking about this whole type of problem from a reaction front perspective. And so in chromatography, a mixture is dissolved in a fluid, and that's the mobile phase. And that carries this mixture through a stationary phase. And the various constituents of the mixture will travel at different speeds and separate due to variable adsorption to this solid phase. And that causes them to separate. So say you've got some solution here, the green solution, I really like this. These things will, given a small amount of dispersion and a background flow that's constant, they will separate at constant distinct speeds and arrive at the end of the column at separate times. And where we get the name chromatography, color, it was originally used with dyes, separating out the different pigments in a single colored dye. And so here's an example of this sort of thing in action. And so I'm going to try to convince you that it's helpful to think about lithological boundaries in some instantaneously melting, porous medium as an effective analogy. So I'm going to think about melt trickling out of some edge of a lithology like a chromatographic column. So that melt from inside the heterogeneity is coming down here and then interacting with the surrounding mantle, which would be the rest of the column. And so these reaction fronts or reacted zones will form as this melt kind of seeps out of this lithological boundary and into the surrounding mantle. And the key to understanding would a reaction front enhance the ability of channelization or be conducive to channelization occurring is, does that reaction dissolve the matrix around it? So is it increasing porosity as it flows? So there's an upstream increase in porosity that's required for hydrodynamic instabilities to occur. So the key to understanding the formation or the plausibility of formation of channels in this specific context is, what's the change in porosity across the reaction front? So this is not like a chromatographic column at all, but it's just a really excellent demonstration of hydrodynamic instability. And so this is two separate liquids that, when they're mixed, they become denser. And so what you get is enhancement of the flow field where these things first mix, and given some tiny perturbations, this flow field will create this sort of self-reinforcing finger-like flow structure. And so that's what I'm talking about when I mean hydrodynamic instability, is the organization of an unstable reaction front into sort of structured fingers. So yeah, so we're thinking right on the edge of this little heterogeneity prior to melting. We've got this step discontinuity, and this is going to allow us to use the kind of theoretical framework that's been developed for chromatographic theory over the years. And this step discontinuity as an initial condition is called the Riemann problem. And some of the ingredients we need for this analysis to be nice and simple is we've got an equation of state that depends on local thermodynamic equilibrium. We have small hydrodynamic dispersion. We're going to scale the problem such that we can approximate the porous medium right at this boundary as rigid. And the reference frame that we're using is going to move with the solid. So we're going to think of the solid as fixed, just like the immobile phase in the chromatographic column. And we're not the first people to think of using chromatography as an analogy for some geologic process. This is Hoffman, 1972, and this is an injection of some KCl to induce ion exchange and feldspars, just theoretically. But what is important here is you can infer the retardation of this reaction front based on the composition of the solid and liquid phases of what's being injected and what's in the background. Well, this is being injected and this is in the background. So you can infer different speeds along the reaction front based on the compositions. And then most chromatographic theory that's been applied to the mantle, starting in 1987 and since then, has been based off of Navon and Stolper, and they were studying the partitioning of trace elements into the melten solid. And so what we have here is, if something doesn't partition into the solid, it'll just flow along with the background melt. Let the tracer, let's say, it flows on this one-to-one line. But with increasing compatibility, you leave things more and more behind in the solid. And so this is sort of a frontal depiction of that, right? So something that's really, really compatible gets left behind, while things that are less and less compatible flow through the box further. But thinking about this in terms of trace elements leads to a decoupled system of linear equations. It's Henry's law. But what we want to think about is the localization of melt flow into channels. So we're thinking about major elements. So we're going to attempt to extend this theory of trace element chromatography to the major elements using some phase rule. So I know I just went over a whole bunch of stuff, so brief recap. This statement of the problem really is like, okay, we're having more trouble making channels than we would like. So how do we make channels? And we're going to try and think about it from a different perspective. So the melt flux in these mantle models was insufficient for those channels, but we've also invoked the idea that fusible heterogeneities might supply that upstream melt flux that we need to make said channels, and we need that upstream increase in porosity. That's the essential piece. And so what we're going to do to examine that is we're going to think about reactive melt transport from chromatographic perspective using major elements. We're going to do this by developing a theoretical framework for reactive melt transport right at those lithological heterogeneities, just like the Riemann problem shows you that initial discontinuity. And then we're going to classify different relationships that heterogeneities and their backgrounds have, and hopefully characterize what types of solid solution mixtures, or at least lithological contrast, would be conducive to reactive infiltration instabilities. So, equations of state. So, the first thing that we need is some equations of state to determine the intensive state of our system. That would be temperature and porosity. And throughout this whole example, we're using binary solid solution with liquid solution. So we're going to use this partially molten olivine forsterite phthalate solid solution. But in principle, there's nothing keeping you from doing other crustal type lithologies that also make solid solution. So we're going to think about the binary solid solution associated with olivine, partly because this is what has been examined the most in the past by some of the modelers I showed you in my introduction. These are in boldface. Hewitt 2010 is these are the phase behaviors he used to calculate what should be on the liquidus and what should be on the solidus in his channelization study. And this here, where I showed that sort of fusible enclave breaking up into heterogeneities from the Weatherly and Katz model, this is what they use, and they use two parallel linear planes to calculate, what concentration, given some concentration, pressure, and temperature, what should be on the liquidus and what should be on the solidus. So we're going to do something similar and kind of analyze the phase behaviors that these guys use, but sort of in a simpler, more analytical context. So the way we're going to draw the phase diagram is this. We've got the fusible end member melting temperature here, and the refractory end member melting temperature up here. We're just going to write it all in terms of the refractory component. So 0 is no forsterite, 1 is all forsterite. And then we're going to draw the liquidus and solidus curves based on the change in Gibbs energy of fusion, both of the end members. So we end up with a liquidus and solidus curve. And then, given some melt fraction and some temperature, obviously we can, on this isothermal chord, say, okay, we've got this mole fraction of forsterite in the liquid and this in the solid. And since this is the refractory end, remember we're plotting this as it's depleted in the liquid and enriched in the solid. So, and then these are our conserved extensive quantities. So we've got basically a pore weighted sum of concentration and enthalpy in each phase. And so this is the pore space, the density of the melt, and this is not the pore space, density of the solid and the solid. And the same with specific enthalpies for bulk enthalpy. The enthalpy of the solid is a linear combination of what enthalpy phases are present. So this would be your refractory end member of the solid solution's specific enthalpy, and it's weighted by the mole fraction of that we got from the function of temperature. And then the enthalpy of the melt is that of the solid plus the enthalpy of fusion. which in principle should also be a function of mole fraction and temperature. But there's kind of a problem with this. For any given composition and enthalpy, you can find multiple temperatures for the same, multiple porosities for the same temperature, actually based on how much enthalpy is present in the solid solution. So essentially, the residual for the equation of state is multi-valued. It's kind of shaped like a piece of DNA almost, right? Like it's curved. So given a single temperature, you can have multiple enthalpy states because the tie lines are nonlinear, and then you could end up with multiple porosities. So I got around to these simplifications that, it's funny, I didn't set out to do the same simplifications that Weatherly and Katz did, but I got there honestly because I ended up with this multi-valued residual function. So these terms are basically taken from or calculated from the Weatherly and Katz 2012 model. Seen a couple confused looks there. All right, you guys so what those guys basically did, and what I'm going to do, is you assume that the melt and solid phases are the same, and that the latent heat of fusion is constant, right? So this is the same everywhere, regardless of what the solid solution actually is. And this is what was in those other papers as well. So I guess in a way, even though we've made the simplification to get around that more complicated reality, we're at least comparing apples to apples. And now temperature is unique given some sort of combination of concentration and enthalpy somewhere inside that solid solution. And so I think it's helpful to replot the phase space in terms of the native variables. So we've got concentration and enthalpy here. The melting temperature has turned at each end member from a singular point to a line, and that line's distance is the latent heat of fusion, and those isotherms have now been tipped up by this difference in the latent heat of fusion. But this slanted line here is an isotherm, and you can think about these curves now as sort of the enthalpy liquidus and the enthalpy solidus. Another thing that I think is interesting is because there's solid solution everywhere in here, the only pure melting solutions are actually on the end members along these pure end members. So anyhow, if we give this thing composition and enthalpy, we can invert for temperature, which is unique, find this chord, and we can plot our porosity everywhere in this phase diagram. So now we have an equation of state that we can solve efficiently, quickly, and know the intensive state of our system given our extensive conserved quantities.
Can I just ask, for those sort of plots, have you checked, do you produce KD, FE, and G of about 0.3? Or is that, so the iron is like many experiments find, iron magnesium exchange between olivine and liquids, there's always the same
Partition coefficient?
Yeah, or partitioning. It's sort of in the background of everything you've done, but I just wondered whether you'd checked whether the shapes of those.
I think later some of the analysis I'm going to try and do might answer that. Right. So maybe sit on that for a little bit and we can come back to it. So I'm going to write down the transport equations now, but I'm going to do it in a way, a very specific way, because remember, even after all of that EOS mumbo jumbo I just went through, we're looking to kind of describe this as a chromatographic column. And one of the key features of those chromatographic columns is small dispersion. So we're gonna, we want to write this down in a way that we have an advection-dominated form to get the full analysis, the full chromatographic analysis of that Riemann problem. And then we also need a length scale that allows for the rigid porous medium, so it can be like the immobile phase in that column. So this is the dimensional transport model. It's just the ADE for composition and enthalpy. But we gotta non-dimensionalize this in a way such that we've got a rigid porous medium. And so we want to adjust pressure to go away from sort of the classical Mackenzie type viscously compacting porous medium type model to something that's just simple Darcy without a moving solid phase. And so we do that by scaling with the length of the heterogeneity against the compaction length. And then we assume that the rheology is some inversely proportional to phi, and we scale this by the by some characteristic permeability and melt flux, and we can actually kind of make the resistance to compaction infinite, and then the Helmholtz equation, that is the Mackenzie style viscously compacting porous medium, then kind of collapses to the Poisson equation, and we can approximate flux as a constant given by G in one dimension. And then we want to scale this on sort of this Q, this advective time scale. So all of our variables have been scaled in terms, all our spatial and time variables have been scaled by the length of that heterogeneity and the Darcy flux. Temperature is just whatever temperature we're at minus that temperature for the first little bit of melting over the entire temperature range. So that's essentially temperature scaled between 0 and 1. Composition has been scaled by the density, which is now equal across phases and components. And enthalpy is scaled by the specific heat of the solid and the liquid, which are now the same, and that whole range of melting temperatures. So then we get a nice dimensionless transport model. This XM comes from our old phase behavior, but this dimensionless liquidus for the enthalpy is now dimensionless temperature plus the Stefan number, the inverse of the Stefan number, which is the ratio of latent heat to sensible heat. And these are the Peclet numbers that I've put in here. I know I'm talking about small distances, which would, of course, make Peclet numbers larger. But these terms here, D and the thermal diffusivity of the liquid and the hydrodynamic dispersion of the porous medium, these numbers are really, really, really small. So the Peclet numbers become really, really, really big, and we can write our advection-dominated form in a nice, simple quasi-linear form, where this U here is our conserved dimensionless quantities, composition and enthalpy, and a nice property of the quasi-linear form for hyperbolic equations written as such is this A here is just the Jacobian of the flux function, so it's just the derivative of FU. So the flux functions are essentially giving us what's on the liquidus. These give us the mobile phase. So like I was showing earlier, we have a residual function here. We give it C and H, we minimize for temperature, and then we can get our XS and our T. And remember, the enthalpy liquidus was just this T plus the inverse of the Stefan number. And something I want to point out is each one of these contours lays on an isotherm. So you give it enthalpy and composition, you come somewhere in here, follow that isotherm out to the edge. That is essentially what's transportable in here. And same for enthalpy, obviously. And what's interesting is these are all isotherms too, but they just happen in different spots. So here's where we are. We're at some little heterogeneity whose length scale is much smaller than the compaction length. we've essentially got no diffusion, and we've got a constant upstream melt flux. So now we can actually analyze this system chromatographically, and we do that via solutions to the Riemann problem. So another reminder is the melt is the mobile phase, the solid is the stationary phase. We've got this left state inside here, which is that, and we're pushing it into the right state, which is over here. And this is written this way, where we have a set of conserved quantities to the left of our dimensionless spatial coordinate, and a set of conserved quantities to the right. And I just wanted to put this slide up here, even though I've shown you the setup a couple of times. I'm going to refer to the stuff inside the heterogeneity, or the upstream stuff, as the left state, and the mantle, or what's intruded, as the right state, as is standard in most chromatographic analysis. So it's the solution to this 2x2 system with conserved composition and enthalpy. Well, we just insert the flux functions into our advection-dominated form, and we've got the quasi-linear form right here, so we just need the Jacobian of this. And I figured since I was at a math place, I'd actually plot the Jacobian. I've never done it before for anybody. So we get the Jacobian here, and the characteristic polynomial of this Jacobian gives us two eigenvalues. These are the eigenvalues. One is always 0, and one is the second derivative of concentration. The other one's the second derivative of the enthalpy planes. And this is what they look like. And essentially what these eigenvalues represent is speeds of simple waves. Remember, I showed you the chromatographic column, and I showed you that green line splitting into a yellow line and a blue line, and then moving independently at characteristic speeds. Well, now we have a solution that's a superposition of two waves. Wave 1 and wave 2. They move independently with the characteristic speeds given by those eigenvalues. These eigenvalues are set by C and H, the conserved variables. This one's always 0. This one, note the nonlinearity of the color bar here too. This one is, pretty much under 1, and then gets really fast up here. And so this independence, right, if they start at the same point, it implies that the waves are ordered from slowest to fastest. So if you had two race cars at the starting line, and they took off and one was faster than the other, you would see an order from the starting line of the slower wave first, and then the faster wave next. And so if you're a little particle floating along from the back, and you're to overtake all of these waves, you would see the slowest wave first and the fastest wave last. And so these solutions, since there's two waves, and they represent some sort of reaction front, you go from your left state along one wave to an intermediate state, along another wave to the end state, or whatever the waves haven't made it to yet. And so in the hyperbolic limit, there are triple valued solutions that are possible mathematically, but these are non-physical. So this would be like saying you had 3 different porosities at one point in space, which doesn't make sense. So we use I'm so sorry about how I'm about to pronounce this, but the Rankine-Huguenot jump condition. Was that good?
Yeah.
Oh, nice. Don't worry about that. Anyways, so this is how this works. Essentially, we're familiar with this to a certain extent, like a water wave. If the back of the wave is moving faster than the front of the wave, you get surf, and it rolls over and crashes and does all sorts of neat stuff. But we're in a porous medium, and that kind of doesn't make sense. What happens is if the back of some wave is moving faster than the front, they meet at a point and kind of push against each other, as you could imagine it, and they move together as a traveling discontinuity. And the way we've handled this is using the aforementioned Rankine-Huguenot jump condition, which is essentially a mass or energy balance of the shock across the discontinuity, and it's written this way, and the flux v over the total change. So, simple waves. Put all the rules up there as a reminder, but so we start with this initial discontinuity, and we get something that looks like this. That first eigenvalue, it's a good time to point out, was 0, right? So we've actually got a wave that sits here. It's a linearly degenerate wave that doesn't move. So this stays through time. By the way, this is our dimensionless time axis, and this is our dimensionless spatial coordinates. So this is evolution through time this way. So we've got this reaction front that just doesn't move, and then we've got this other moving reaction front that essentially moves with this characteristic speed, and although it stretches out a little bit as this thing goes forward in time, it never changes its actual shape. And so this I've plotted just in the concentration, but there's a coupled enthalpy variable too, right? Like I could just have two on top of each other. But since this thing never moves, and this one does, what's left behind is this constant intermediate, not necessarily intermediate actually, but this constant reacted zone. Okay, so this sort of pattern will be evident for all solutions to the eigenvalue problem. And so if we've got this characteristic speed and we've got this characteristic reaction front shape, can we plot how a reaction front given, end states, circle and triangle, can we predict how this should go through this phase diagram? And the answer is yes, is the recognition of that characteristic shape allows for the introduction of a similarity variable. And so what can happen then is this can be collapsed in time and space here to just be plotted as one characteristic curve, where, as I told you, this wave W1 is always 0, it sits at 0. This intermediate state here stretches out until you get to a wave 2, which has a characteristic velocity, in this case, of right about 1 here. But this collapse here allows us to reduce the system of PDEs to a system of ODEs, and we can recast this system. And remember the eigenvalues we have here, but now that we've got ODEs, we can solve for the eigenvectors. And the non-zero eigenvectors, right, if we just plug in 0, that gives us the eigenvectors for these constant flat states. But the non-trivial solutions to the eigenvectors will give us sort of the directional conservation given 2 points inside the solid solution. And so what I mean by that is there are these pathways that exist in this concentration enthalpy phase space. And so the way you can think of this is this direction from this circle. I can move incrementally, infinitesimally, in this direction and this direction only along that first wave without violating massive conservation and energy. So this is the eigenvector associated with the first characteristic field. It's given R1. And this is the eigenvector here associated with the second characteristic field, R2. And what's interesting about these eigenvectors, or why I'm introducing them, is because you can integrate them. And so these integrated eigenvectors will intersect at points, and those give you the 2 possible intermediate values of the reacted end state. And so then you can plot those guys and throw everything else away. So if you started with circle and triangle, the only way to get from circle to triangle is either to go from circle to diamond to triangle or from circle to square to triangle. I know that's, funny notation or way to say it, but these are the pathways given these two end members such that you don't violate conservation of mass and energy. And one more thing I wanted to point out is this plot here, it's 0 everywhere. So I've essentially superimposed it on top of this one. So I've just got the pathways for that 0 velocity wave here, but the eigenvalues, the actual wave speeds for these longer pathways is plotted down here. So now what the question is so if I have circle and triangle, do I go to diamond to get to triangle, or do I go to square to get to triangle? And I'm going to show that if you start at circle, you have to go to square to get to triangle. I'll show you why. So we've got all the ingredients we need to make this, this solution structure complete. We've got the eigenvalue problem for continuous solutions. We've got the Rankine-Huguenot jump condition for discontinuous solutions to the problem. We have reaction front velocities, or velocities associated with the Rankine-Huguenot jump condition. And we've got our allowable pathways, our safe pathways through composition and energy phase space. So at this first reaction front, there's an isothermal jump, and it's linearly degenerate, and we reassign it the variable C1 for contact discontinuity, 1 standing for first characteristic field. But this is linearly degenerate in temperature, and this wave, the physical interpretation of this wave is it arises because we've enforced local thermodynamic equilibrium, but we've also given this sort of Riemann problem that has a discontinuity as the initial condition. So this first wave essentially adjusts circle to square such that square, this middle state, can connect to this end state along some moving reaction front. And then for the second characteristic field, it's a little more complicated because you don't know if you have a continuous solution to the Riemann problem or if you have to use some sort of shock approximation like the Rankine-Huguenot jump condition. And what I'm going to say is the flow direction matters. If you're to pick some point along the same wave and flow up this way, you get a smooth spreading wave that connects both of the end states, shown by this triangle, diamond, and square. However, if you flow the other way, you get these discontinuous moving shocks. So the way you can think about it is this way, and I kind of use this in my intuitive water wave discussion. Here, this eigenvalue is bigger than that eigenvalue. So the back of this wave is moving faster than the front. But here, the front of the wave is moving faster than the back. So that's more like the fast and slow race car analogy, right? So you've got the back of your wave, putzing along at this speed when the front of your wave is going maybe this speed. So you get this rarefying spreading morphology, which we denote R for rarefaction, and we're going to call these guys S for shocks. Oh, there they are. Nice. So what this means is for even just those two end members, the direction of flow from left to right actually dictates the reaction front morphology. So if I put my left state, so what I'm injecting, my mobile phase, if this is my left state and this is my right state, we go along that isothermal jump to square here, and then there's a continuous solution along this integrated eigenvector to the triangle state here. But if I start at triangle, and try and get to circle, I jump along this isothermal pathway as before. However, I've got some wave that's moving faster at the back than at the front, and a shock is formed. And that's shown here, triangle, diamond, circle, for both of the conserved variables plotted against the similarity variable So the kind of summary of all this structure stuff is that we get two reaction fronts, and the first reaction front doesn't move, and that actually necessitates this constant reacted zone. The second reaction front can either be spreading or sharp, which is somewhat important to thinking about the types of channelization processes that you might want to have occur due to some sort of frontal reaction. These reaction fronts, they don't change with time. Mass and energy are conserved, but it's restricted to these pathways through phase space that must be adhered to. And since conveniently we have that zero solution, we can kind of imprint all of the possible solutions and pathways onto one diagram. It can be collapsed. So we're going to use that sort of collapsed phase space to characterize these essential behaviors. And so we're back to reminding you that this left state is being injected into the right state, but we're getting to the motivating question now, right? Is this lithology here, is this conducive to creating an upstream increase in porosity? So is there melting and dissolution, or is there freezing and precipitation along these wave paths? And to understand that, we just track the changes in porosity along that second wave, wave 2. And so this is sort of the summary of the analysis in a picture. Here we've got the porosity contoured in gray. And the solution to the eigenvalue problem is here in gold, but the shock locus, or the equivalent of the integrated eigenvectors for the shock, actually just lies, it dovetails on these curves. So if you're going with the arrows, you have a continuous solution, and if you go against the arrows, you have a shock, a discontinuous solution. These teal lines are the integrated eigenvectors for the first characteristic field. Those are always 0, and these also lie on isotherms. So just like I was showing you, you could plot your point here and your point here, and you could know that to increase in speed, right, the eigenvalues must be ordered from slowest to fastest. You would have to go from here to here to here. Because if you went from here to here to here, you would make a triple valued solution. And another thing that falls out of this is we can plot the retardation. So this is like what Hoffman did, is you can infer the retardation of your reaction front as a function of the solid and the melt concentrations, or what they're composed of. And so for a constant porosity, the retardation function is given here, where it depends on the slope of this kind of, it looks like an isotherm. It's not really one, but this slope of this isotherm-ish rose boom diagram that compares the composition of xm as xs as a function of xm. And so we want to know, along a fast path, are we dissolving the matrix reactively as we go? And we can answer that question by saying, okay, is porosity higher here at the beginning of my moving wave, or here at the end of my moving wave? And I'll show you a little more about that. So I'm plotting porosity here. And there's actually one last interesting feature that kind of falls naturally out of all of this, is there's a point here where the behavior of the binary solid solution kind of flips. So I showed every example leading up to this here, where if you go from circle to square to triangle, you always get a contact discontinuity, a rarefaction. And if you go from triangle back to circle the other way, you get a contact discontinuity and a shock. But down here it's the other way, where you would get a rarefaction on this top curve here and a shock on the bottom curve. So the behavior switches directions. And these two that I've plotted in red, now this one here and this one here, those result in upstream increases in porosity, which you have favorable conditions to channelize melt. And so I'm going to kind of show the difference between these two things here. And one more thing I want to point out before I show my little movies and kind of wrap up. If we linearize these phase diagrams, you lose the fact that these phase behaviors might flip, and you wouldn't get any sort of rarefaction at all. You would simply have shock solutions everywhere, and that might affect the way that these larger simulations what they're outputting. That there might be some intrinsic spreading due to the reactions that live on the back end in this phase behavior, and maybe we haven't realized it because we haven't thought about it that way yet. So, and then the other thing too is everyone likes to choose their compositions and their temperatures and enthalpies and stuff so that they're far away from the end members, because they want the latent heat of melting to be small, compared to the rest of the energy budget. But then that puts you in here where it's ambiguous whether a certain type of reaction front would create porosity or not. So it's kind of, I don't know, strange way to think about it, but it makes me wonder what's really going on due to chemistry in the middle of all of these phase diagrams. So the whole point of this was to extend this to higher dimensions and see if those little 1D plots can predict some sort of channelization, like some simple 2D simulation. That was the goal. Want to see if the interpretation of those chromatographic pathways works. Here I'm just putting up, we used the same dimensional variables that Katz and Weatherly used, just really middle of the road type stuff to make these little movies here. And so this is the first reaction front I'm going to show. It was the triangle diamond circle, so that was the upper pathway and that little suite of pathways I showed a bunch of times. And this thing looks like this. So this porosity wave creates an upstream decrease in porosity. So as this thing is flowing, it's freezing and precipitating melt. So it just kind of plugs itself up as it goes. It's a self-limiting flow. This guy, on the other hand, so even though this intermediate state is lower than it would be, the porosity would be inside the heterogeneity, it does create a porosity increase compared to the triangle state here. And so that looks like this. And one thing I want to point out is, since we've got this spreading behavior instead of the shock, with time, these channels become more and more diffuse, right? So these rarefaction type waves are intrinsically stabilizing type mechanisms. You can still have these instabilities that are kind of smearing as they go. And I don't really know if this is a feature that's discussed at great length in the literature. I just think that it's an interesting point that if you were going to linearize your phase diagram, you would never ever observe something like that. So this is using so all of those examples that I showed, so it was like easy to see inside the phase diagram, were like really, wonky melt fractions, up to 30% and stuff like that. But now let's, take it back so we stay all within, 0 to 3% melt fraction. And these are the pathways plotted here inside an inlay of that bigger phase diagram. And I just wanted to point out again that we can make these instabilities right at this lithological interface in 2D with some little perturbations to the flow field to start, but they do become really, really diffuse because this is a rarefaction pathway. So these channels would stay much, much sharper if we were creating porosity along one of these shock pathways. So yeah, what I've been been saying here is kind of, could we get diffuse looking channels from moving this way on some spreading wave that increases porosity upstream? Certainly, if we chose a composition down here, we could increase porosity with a shock and make tighter, less diffuse looking waves. And then this one, there's a lot going on in this plot, so I'm not going to go all the way through it, and I'm just going to kind of stop here. But also, using fusible heterogeneities to see mantle channelization also implies this, which is a refertilization of the mantle, and that is not what we see at dunite channels, right? The dunite channels themselves are more refractory, so I think that kind of implies at the end of all of this that using a binary solid solution with liquid solution is a very poor choice to look at mantle dynamics. So I'm just going to stop there, and I'll take questions.
Thank you very much, Jacob. Questions?
Can you just put that last slide on? I just want to look at it while we're talking.
If you've got multiple components, presumably, say if you had, so at the moment you've got binary solutions, so you've got a ternary, would you have 3 waves?
Yeah, but the first one would be stationary.
Right,
Yeah.
and then you'd have 2 moving waves.
Yep.
Would anything interesting?
Well, what would happen then is the constant state reactive zone that you left behind would be different, right? So here, this was a really nice example because your moving wave goes through, and you're just left with this state that is, kind of untouched, and you have sort of a remnant of your initial condition left behind. What would happen if you had another wave is one would sweep through, and then the other would sweep through, and then you have a different reacted zone left behind. But what's interesting about this type of analysis is you don't know if, given the initial conditions, say they were more complicated, say it wasn't the Riemann problem, if you had a faster wave arise behind a slower moving wave, they would interact and kind of kill each other. And so I've done, and maybe I can dig one up and show you, but if you do sort of a hat initial condition instead of a Riemann initial condition, you can make a shock that moves and that later gets caught by a rarefaction, and then they essentially kill each other off to 0. So you can have that sort of whole diamond filled up. You go around the whole thing, and then they eat away at each other until they end up on just one of the fast paths, and then they just like die off into the background state. So you can make it as complicated as you want. It can be cute, but.
So Jacob, your criticism on binary solutions and that I got, but is there any hope to test this empirically in reality? If I go to the mantle in Oman or in Talkeetna or whatever, have these people reported fronts in these rocks or any trace of fronts propagating or?
Well, I think you could measure the variation in compositions, along a dunite channel, maybe from the center to the edge, and see if it looks like there's any sort of rarefaction or abrupt change that could be interpreted as a shock front. But
it's very sharp edge.
Yeah, exactly. So I think what it could be is some sort of frontal reaction. The other thing that I didn't really talk too much about is you can plot 2 points that are both comfortably inside the phase diagram, and their intermediate state, where their eigenvectors would intersect, can be outside, right? So they might necessitate an intermediate state that's all solid. So you could get some sort of shell that's necessarily formed at certain lithologies, right? So you push your porosity down to 0.
What's the length scale of these fingers?
Oh, yeah, so in the calculations I put up here, we had the length scale of the heterogeneity being 20 meters.
And it's that scale.
Yeah, but I mean, really, we were just looking for something that's smaller than a compaction length, which we chose to be 100 meters.
Right. You were doing the analysis all in the kind of infinite compaction lengths.
Right,
limits.
right,
But
right,
these,
right.
these simulations are finite compaction lengths.
Exactly.
All right, okay.
No, and then we approximate it as infinite compaction length because it's scaled as the length scale of the heterogeneity squared over the compaction length squared. So if you've got 20 meters over 100, you've got like 0.04 or something. So that can kind of be neglected.
Yes, sorry.
So just so I understand, so you're saying if I did these exact same calculations with the Katz and Weberly phase diagram, the main difference is the sharpness of the channels, or
Yeah. So what I'm saying is the this sort of diffuse looking, I guess, morphology comes from the fact that you've got this spreading wave along this pathway that is increasing in the porosity upstream. So as this thing is dissolving porosity, it's sort of spreading out too, which is a stabilizing mechanism, which is why this looks diffuse. But if you make these linearized phase diagrams, you would have linearized porosity profiles, and all of your pathways through that phase space would be linear. So you would have that linear degenerate solution that just sat on an isotherm, so it'd just be a line straight across this, and then you would just go across some flat plane that mimics this flat liquidus. So you would just get not moving shock every time. So you wouldn't get that you wouldn't get this sort of bleeding looking disperse type finger to the limit of the intrinsic hydrodynamic dispersion of the porous media, of course. But the whole point is you would necessarily build sharper and sharper features doing something like this. The nonlinearity is, in a way, intrinsically smearing.
John?
So the Dunite channels in Oman, I mean, what you're really seeing there hasn't really got that much to do with, you said this at the end, but it's the binary solid solution with perfect solid solution between them. The reason you see them is because you've had a reaction that's eaten pyroxene and precipitated olivine, so it's like a eutectic or peritectic system.
Exactly.
So have you tried to look at that?
Yeah, I mean, so the short answer is yes. This makes for the more interesting analytical study because this is mixing, right? The channels in real life come from unmixing, right? So, given some temperature, you're just separating out and you've just got a lot of linear type reactions too. Almost linear in the way I was talking about here, where you would just have a bunch of discontinuities moving around as little shocks. But, that also, thinking about it from that angle, does seem to make sense when you see how sharp all the boundaries are in those Oman ophiolites, if that makes sense.
Well, it's the thing that lets us see the channels in the end. I mean, whether it's the cause of channelization deeper, I don't know.
Yeah.
But that's the end point. It's what it's the observation that people try and keep on hitting. So you wouldn't really expect this sort of analysis to be able to reproduce the field observations.
No, not at all. And that's sort of, it kind of took doing the analysis to make me realize that, right? Like, I started reading, papers early on in my PhD, and people were like saying, okay, well, we want to observe some behavior in the mantle, some phase behavior, and it's mostly olivine, and so we're going to use olivine. And that seemed, sensible. But I think that the key features, if you're worried about channelization, aren't mixing, which this is doing, it's unmixing.
Yeah. I mean, the other sort of related point there is the heterogeneities that we're thinking about. It's not that there's like a patch of mantle that's got iron-rich olivine next to a patch of mantle that's got magnesium-rich olivine. Is that there's a patch of mantle that's got large amounts of calcium, aluminium,
Right.
content, maybe some water, maybe some CO2 versus
Well,
an olivine-rich mantle.
So that olivine mantle type explanation that you just, juxtaposed against sort of your worldview is the way that, man, I have a lot of slides. I mean, that's the way that these work. this one, this paper, this picture of the mantle was calculated using binary phase diagram.
Exactly.
Yeah, so instead of these channels being refractory dunite channels, right, these are kind of the opposite. These are like fertile channels.
Mm.
So, I mean,
Yeah, but it's worse than that because this is still is a binary system, but the sort of heterogeneity that we think really matters is in, you know, at least ternary. You know, it's in
Absolutely, yeah.
multi-component. So
yeah, no, it would definitely be significantly more difficult to extend the analysis to, you know, incorporate that sort of thing, but in principle can be done, would be, you know, pretty much the same type of analysis. But say we added one more component, you know, we'd have a 3x3 matrix with different derivatives to the flux functions that depended on more things. It could be done. Taking the derivatives that I needed to do the Jacobian of the flux functions was pretty involved, but you could do it.
But would there be difficulties associated with the topology of a different phase diagram if it is a eutectic?
Oh, yeah, that's true. So say, for example, if you made a ternary diagram that on each leg of the triangle was a perfect solid solution. I know that's not exactly what you're asking, but if you did, you'd be under constrained using the same methodology. You could only predict a locus of possible solutions. You couldn't point to one, right? So depending on the way that you combine the different phase diagrams, you can run into uniqueness of solution issues, if that's what you were asking.
Do you have any further questions, Jacob? In which case, can I thank Jacob once again? Thank you very much.